Hey everyone, Hour 4 AP Physics here, and we have a challenge today in which we need to determine the ratio of heights that two toilet paper rolls need to be dropped so that when they hit the ground at the same time.
The catch is one of them is simply dropped while the other one has its end held up and rotates as it falls to the ground. This causes it to move slower because some of the energy is put into rotating the object.
So how do you suppose we do this?
So to solve this problem, we need to use a few equations. First of which being potential energy of gravity. We also need to use both translational and rotational kinetic energy equations, as well as some basic kinematics.
It's just plugging in using basic kinematics, find the free falling, the time it'll take for the free falling object, and then solving for t squared. So you take the basic kinematics equation for position, plug in your variables to solve for t time squared. That's the first part, second half. So the second part, you find the total energy that it starts out with, which is just the potential energy of gravity. You start out with the potential energy of gravity of the second roll. And you have to set that equal to the sum of kinetic energy translational and kinetic energy rotation. Then you just plug in the equations and you plug in the equations for those two. Then you cancel. Then you can. Then I put in the. So you plug in those two kinetic energies, the equations for that. Next I put in the next thing I did was I put in the moment of inertia. Canceled out some things. I put in the moment of inertia and then canceled out mass. Multiply each side by 4. Then I plugged in acceleration times time. Then I plugged in acceleration times time for linear velocity. I plugged in acceleration times time. And then I plugged in acceleration times time divided by the outer radius for angular velocity. At that point, it's just simplifying it down and solving for time. So then you just have to simplify it down and solve for t squared. Then you set the two. So you set t squared. You take so now you take the earlier equation from the first roll, because you know how we solved for t squared up there for the first roll. Set that to the t. That's the same t squared as the t squared from the second roll. So you set those equations equal to each other. Then you solve for height of, and then you just solve for the ratio of heights, and then plug in. No, you solve for that, and then you plug in your values for inner and outer radius. That's the really oversimplified version.
Four.
Is it recording? I don't care about countdowns.
3, 2, 1, go. Oh, that's not good.
Yeah. Let's re-roll that up.
Double check the height that's on that.
Oh.
Go. Yeah, no, we're not showing that in the video. We're deleting that. We're deleting that. We are deleting that.
So, what do you think about the experiment?
So I think it went well, however it wasn't quite perfect. As you saw in the video, the free-falling one hit the ground a little sooner than the one that was unrolling, but there could have been quite a few reasons for this.
So what do you think went wrong?
So we had to make quite a few assumptions while we were doing this test. We had to assume that there was no friction or air resistance on the rolls as they dropped, and we also had to assume that both the radius and mass of the unrolling toilet paper didn't change at all as it fell, even though, as you could see in the video, there would have been slight changes as it falls.
So do you think this experiment was a success or a failure? What are your thoughts?
I mean, I think it went well. However, I don't know if we could call it a true success. However, human error could have played a huge part in it as well, with both the measurements of the toilet roll as well as getting exact drop heights and drop times could have been off a little bit. And I'm sure if you played back the video in slow-mo, there would have been slight differences in the time they were released. So I think it overall went well.
I do too.
Anything else?
Not really.
All right.
And that's it.